All right, folks, I am going to talk through the problem that we did this week where we're trying to figure out how much energy we lose simply by breathing. So I've already set up the problem for you here on the screen, the diagram, where we have three streams, two streams coming in. We have stream number one is dry air. We're assuming it's just pure air, no water, at room temperature, 25 degrees C. And we're assuming the standard breathing rate, volumetric flow rate of about 6 liters per minute. And we're assuming that water evaporates from the body. And then, therefore, when you breathe out, you now have dry air, but it's saturated with water at 37 degrees C. And I'm not going to show how to do this, but if you do the mass balances correctly, you can show that the mass flow rate of the dry air coming in, and this is assuming the ideal gas law, and then taking into account its molecular weight, is 7.0770 grams per minute. And the mass flow rate of water in stream 2 is 0.2916 grams per minute. You can show that by the mass balance. And both of these, of course, these are the in mass flow rate of stream 3, you have the same flow rate of air in stream 3 as in stream 1. And the same flow rate of water in stream 3 as you have in stream 2. So we're operating at steady state. Now, the next step is to consider the energy balance equation. So I've already written the general energy balance equation. And first of all, we're going to assume that the process is at steady state, which means that the entire left-hand side, the accumulation term, is 0. Over here on the right-hand side, if you look at the kinetic energy and the potential energy changes as we are breathing, they're both going to be 0. Potential energy 0 because our mouths are at the same elevation relative to each other when we breathe in and when we breathe out, in a typical situation anyway. And roughly speaking, the kinetic energy there that we're breathing in is pretty much the same as breathing out. So that's where we're assuming those two terms are 0. Two sets of terms are 0. And then the other term to think about is work, but that's going to be negligible because if you think about it, it's really potential energy changes happening there with respect to the lung. And those are going to be quite a bit smaller than the latent energy changes that are taking place due to the fact that we are essentially converting liquid water that's in the body to vapor. We're going to assume that's 0, and so you end up with a simplified energy balance of delta H is equal to Q. So what I've done now is set up a table. When you start to get into these more complex problems, and this is just getting on the edge of where you kind of need this, this is called an NH table, and that stands for molar flow rate and enthalpy table. In reality, I'm doing mass flow rates on this table, same concept. So first what you have is you list the species. You have a row for each species. So we have water and dry air. And then very important, you have to establish a reference date. So here for water, I've picked a very interesting looking reference date. It's essentially the reference date for table E5 in your book. And for air, I decided I'm going to assume that the heat capacity of air is constant. I'm just going to pick a reference date for air that makes life easier for me. I'm going to pick air as a gas at 25 degrees C, 1 atmosphere. So to fully establish a reference date, you want to say the compound, the state of the compound, is it liquid, gas, or solid? What's its temperature and what's its pressure? Okay, so for air, I'm going to pick the state of the air as we breathe it in. So that allows me to go over here and say that the specific enthalpy of air is 0. And so, as you can see, I have a set of 3 columns for each stream. And so for each stream, I'm keeping track of the mass flow rate, the specific enthalpy of each species, and the total enthalpy of each species. So air, we know, I've calculated before, I didn't show how to do this, that the mass flow rate of air entering the lungs is 7.0770 grams per minute. But the specific enthalpy is 0 because I set that as the reference state. So the total enthalpy of air relative to the reference state that I've established for air is 0. So really, the the work that has to be done then is to figure out what the specific enthalpies are for water in stream 2 in stream 3 and what the specific enthalpy of air is in stream 3. So the way you do that is for example, for water, we're going to let's figure out the specific enthalpy of water in stream 3. So first of all, the actual state of water in stream 3, I've already written it down. It's water. And why I keep saying that it's water will become clear when we have reactions. It is a vapor. It's not a liquid or a solid. It's at 37 degrees C, and we're assuming it's saturated, which means its partial pressure is 0.0628 bar. So what can we find in the steam table? So we know the actual state of water in stream 3, and what you can find in the steam table is, sure enough, of course, it's by definition, we're looking at water, and you can find it at 37 degrees C as a vapor and saturated. Okay, so we're in good shape. We can find out the exact number we want in the steam tables. Now, in reality, fibbing a little bit because the steam table lists 36 degrees and 38 degrees C, so you're going to have to interpolate between the two. The enthalpies are 2567.2 joules per gram and 2570.8 joules per gram. So if you interpolate those, basically take the average of these two, because 37 degrees is smack dab in the middle, we find out that the specific enthalpy of water in stream 3 is 2569.0. So we can go back and update that number on the chart. So we have 2569.0 joules per gram. Now we need to find out what the specific enthalpy of water, the liquid water at 37 degrees is. So we go the same process. Well, at the steam table, we can, of course, find, it's by definition about water, and we can look up water at 37 degrees C, and we can find out when it's a liquid. Now the problem is the pressure there is 0.0628 bar. So it's not quite the number that we want, because there is this one difference. And again, the table actually shows 36 degrees C and 38 degrees C. So we're going to have to interpolate between the two. But the question is, what is the, so we can, the number that we come up with, so let's start with this. If you look in the table, we have 150.7 joules per gram and 159.1 joules per gram. So if you take the interpolate at 37 degrees C, it's going to be 154.9 joules per gram. Now the one kind of subtle caveat here is this is for the pressure at 0.0628 bar, and we need it at 1.013 bar. However, as I've said many times, in class delta H, when you have a pressure change, is very small. So we can go ahead and use this as our specific enthalpy for stream 2. So let's go ahead and update that chart. So we have 154.9. So the last thing we need to figure out is the specific enthalpy of air in stream 3. Again, using the same approach. First of all, I've already mentioned that the actual state of stream 1 is air as a gas at 25 degrees, 1.013 bar, and that, by definition, is the reference state. That's how I set it up. So what this means is that the specific enthalpy of stream 1 is 0 because it's at its reference state. So now we need to figure out compare the actual state of air in stream 3 to what its reference state is. And as you can see, there's no change. It's air in both cases. It's a gas in both cases. And there's no difference in pressure. So the only difference is a sensible heat change. And so we can easily calculate what the specific enthalpy of air is under these conditions. It's going to equal to the specific enthalpy of air at its reference state, which is 0. And we go from the temperature at the reference state, which is 25 degrees C, to its actual state in stream 3, which is 37 degrees C, and we integrate that with respect to temperature, Cp dt. And we can look up in the table, E2, I believe it is on the book, and we can find that the heat capacity of air is 29.07 joules per mole degree C. And we're going to assume that it doesn't change much when it's going from 25 degrees to 37 degrees. So this is a pretty good assumption. So we can figure out that the enthalpy, specific enthalpy of air in the exit stream, stream 3, is 29.07 joules per mole degree C, evaluated from 25 degrees C to 37 degrees C. That equals 348.84 joules per mole. But we want to have joules per gram, so we know that there's 1 mole for 28.84 grams of air. And so we end up with 12.0957 joules per gram equals the specific enthalpy of air in stream 3. So we can go ahead and update our table with that information. Now, we have pretty much everything we need to solve this problem. So what you can do, basically this table is set up so you multiply the mass flow rate times the specific enthalpy, and that equals the total enthalpy. So 7.077 times 0 is equal to 0. 0.2916 times 154.9 is equal to 45.1688. And the units of this, if you think about it, it's going to be joules per minute, using the same units throughout this table. 0.2916 times 2569.0 is equal to 749.1204 joules per minute. And 7.0770 times 12.0957 is equal to 85.6. Whoops. 013. So now what you can do, if you think about it, if you add up these two numbers, you add up all the numbers in the column. Right now there's only one. And they're going to equal the total enthalpy in stream 1. And so this is the total enthalpy in stream 1. This is the total enthalpy in stream 2. If you add these two together, they're going to be the total enthalpy entering the system. And that is equal to 45.1688 joules per minute. Having troubles with this pen here. And then same thing here, if you add these two numbers up, you can add the total enthalpy out. And that is equal to 834.7217 joules per minute. So now we have all the information we need to use the simplified energy balance. So here is the simplified energy balance for this system and for this problem. We mentioned before is delta H equals Q, but delta H is a very concise way of expressing what this equation is all about. So you have to break it up into the individual species flow rates and specific enthalpies in each stream. So delta H equals Q really means the specific enthalpy of air times the mass flow rate of air in the exit stream, plus the specific enthalpy of water times the mass flow rate of water in the exit stream. So this is the total enthalpy out, but I've just said that is equal to, because I got that from the table, 834.7217 joules per minute. And the delta H is also, you have to subtract the total enthalpy in the system. So that's going to be the specific enthalpy of stream 1 times the mass flow to stream 1, plus the specific enthalpy of 2 times the mass flow to stream 2. And that is the total enthalpy entering the system. And as I already calculated on the table, that is 45.1688 joules per minute. And all of that is going to equal to the heat that was transferred to the system, which is the air, and that heat that's being transferred to the system is coming from our body. So that's ultimately how much energy we use, that we lose due to heat transfer to the air that we're breathing in. That's how much we lose. That was sort of the point of this problem, is to figure out how much energy we lose by heat transfer due to breathing. And so what we end up with, if you solve this equation, is that 789.5529 joules per minute. And then we want this in food calories. So we know there's 1,055 joules for 232 calories. And we know there are 1,000 calories per food calorie, which is usually written as CAL with a capital C. We want to get this on a per day basis. So we know there's 60 minutes per hour. And there are 24 hours per day. And when you multiply all of that out, I end up with Q equals to 250 capital C calories, food calories, per day. And so that's about 10 to 15% of our total caloric intake per day. Simply going to, essentially one of our functions in life is to vaporize water. So how about that? And we use about 10% of our energy to do that. Vaporize the water that's in our body and expel it by breathing out. Now that is the end of this problem, how to estimate how much heat we lose due to breathing. And it is a really good example of solving an energy balance that does not have reactions in it. Important things to keep track of here is pay close attention to reference state. You have to establish a reference state in order to solve these problems and break down the problems down to the very fine granular level, essentially, of figuring out the specific enthalpies of each species in each stream and the mass or molar flow rates of each species in each stream, keeping track of all that in a table. And ultimately, once you have them all figured out, you can pop them into your simplified energy balance equation and solve for whatever it is you're trying to solve. And if you do it that way, no problem will be too complex for you to solve. All right, I'll see you next time.